So if you're like me, you just got an alert that there's a severe weather warning and some tornadoes potentially in the area. So if we all go down, at least we're doing what we love, which is talking about production machine learning and pipelines at 4 p.m. on a Thursday. Yeah. So I'm Justin. If you didn't attend the keynote, run Cloudera's Fast Forward Labs organization. Shameless plug, you should follow me on Twitter because I have lots of opinions and I like to write them out. But in all seriousness, I have a really awesome team and I spend a lot of time trying to get the word out about what they do, which is research and intelligence and communications and coordination of the process of machine learning in enterprise. So we have a lot of opinions about things that might matter to many of you in the room. So before I get going, I'll tell you a bit about the background and why maybe I have some things that might be useful. I've actually had a pretty strange background. I started my career in the military, and that might be relevant in this area, maybe not so much in California where I live. But I ended up working in intelligence and communications, so did a lot of big data processing before there were compute and storage solutions for big data processing. So a lot of the problems of deploying into production was my job. And from there, I got a chance to come into consulting and work on really helping people to understand how to transform organizations. And then I went into Cisco and started working at the edge, which has been really relevant recently. And then finally, before coming to Cloudera, I was deep in product and IoT devices because I worked for Fitbit. And I'll probably bring up some stories about how important it is to actually decide to deploy machine learning models before you build a bunch of machine learning models, because I was head of applied machine learning there. Like I said, you can follow me on Twitter, and I'll tell even more stories there. But before we get into the core of the talk today, I want to kind of come back to what Fast Forward Labs does. So we've recently released a number of reports around learning with limited labeled data, which if you were here before, my colleague Nisha did an amazing job of talking about. Before that, we did some work around federated learning. So federated learning, is, if you don't know, is a way to do distributed machine learning. And just like we're in a data center and you get the advantage of the hyperconvergence occurring, but you don't actually have to have the data in a single data center. You can put it at the edge, train at the edge, use it to avoid privacy concerns or some of the challenges and expense that comes with moving data over small pipelines. And then we did, a while back, some work that's very important nowadays around explainable AI and interpretability of models. So this is cracking open the model and understanding how it works, specifically for the record level and also at the system level. And if you've been following the news, you probably know why that's important to be able to do. If it's not there from a legal perspective now, it's about to be. And so if you're building anything, whether or not you're maintaining it or you're responsible for developing the model, this is going to be something really important. So check out what we do. We're always trying to make sure it's relevant. Hit us up and let us know what we're doing well and what we're not doing well. So just to recap, I think everybody probably knows that this machine learning capability is here to stay. But one of the things that I want to pull out, or I always like to pull out when I talk about this, is that most of the transformational outcomes that you see didn't start off as a machine learning project only, right? They didn't start off as a model, and then that was the only thing they wanted to do. So when you think about Google, it's probably the best example of machine learning being embedded into daily lives is Google Maps. You use that every day for all kinds of things, and they've got multiple machine learning models running in production with sub-second response times, and you have no idea that they're happening. So think about it from a route optimization perspective. Those are models there. From traffic prediction and traffic analysis, there's models there. Congestion, all there as well. But they made sure to invest in the ability to be able to deploy multiple models in an application environment that was really beautiful and really comfortable for users. So you're not thinking about all of the software engineering headache that goes into deploying each one of those things. In fact, they're focused on giving the developers a great experience so they can get their output directly to the customers. Same thing with Apple in the iPhone environment. Same thing with Android. It's a platform in itself in that it allows machine learning capabilities to be embedded into the use. And so when you're doing autocorrect or when you're using the facial recognition technology to open your phone, again, the entire platform, the entire software ecosystem had to be designed to make that easy to do. So hopefully I can move through. So Hillary had this slide up, but I'm going to revisit it in a slightly different context. So what I like to tell, especially people that have a lot of background in the platform, in engineering is that there's some good news, actually, about machine learning and AI. The things you're probably feeling is this is going to be really hard. Data scientists are coming in, they're breaking stuff. They don't really understand compliance and governance. But the reality is, to be successful at the top of this pyramid, you have to be really great at the things beneath it. So having a strong background in platform, having a strong background in BI and analytics is actually really critical to being able to do automation in machine learning and AI. And I think it gets lost a little bit that we're on the same team. We have to be on the same team, because if bad data goes into a machine learning algorithm that then gets deployed to billions of users, really negative things can happen very quickly. And so I just want to always start off my talks with, bring everybody back to the center and understanding that we're building a holistic product and not individual pieces that aren't supposed to work together. So with that, let's talk about what production machine learning actually is. So to me, production machine learning is really focused on the technology, the process, and the people that are required to take a machine learning experiment or a set of exploration and to move that into a software application that can be deployed, maintained, and operated over time. And so a lot of the same principles that you may be familiar with in software engineering are going to get repeated here, but they'll have slightly different context, specifically with regards to having feedback loops in place to be able to change the model when the data changes. So just to walk quickly through this simple diagram, you take inputs from business or from data engineering, so that's existing pipelines. You do some kind of exploration, so this is the practice of data science. So you might start with doing distributions, data exploration, and eventually you might get into a place where you start to fit some mathematical functions to the data. So you're writing a model. Somehow, after you've gotten to that place, and it's probably in a notebook, let's be honest, you're gonna have to package it up in a consumable format, something that a machine understands and can deploy or move around just like it can with data. That's when things get weird. So machine learning models don't have a specific format, and we'll talk a lot about that later. But from a process perspective, whatever you do here has to be reproducible, because the moment the data scientist either doesn't have the skills to go farther, which is very common, or they drop it off and give it to a data engineering or an IT team, it has to be able to be recreated for testing purposes, if nothing else, just to make sure it's working. And because we don't have standard formats, this is a really important place to spend some time planning. And guess what? People don't really do that. So a lot of pain comes out of it. So once you have a package, once you actually have a representation of the model, of course, you've got to build a pipeline to run the model whenever it's necessary, whether that's via API, and you want to return a result every single time it's queried, or if you want to run it in a batch format, which means basically there's a specific set of time, and you want the model to run and score some new data every time that time comes up. Now, there's some stuff that I think a lot of people in the machine learning context probably forget, which is that you probably are going to, if you do deploy in an enterprise context, be aware of adversarial attacks. So it's just like any other piece of software. That's human nature. It's certainly the nature of technology. People are going to try to attack it. And probably what you've seen lately happen is that there, especially in image processing, are an entire class of machine learning algorithms that are designed to defeat image processing tools, right? And generative adversarial networks are becoming a key tool of both defending against that and also attackers themselves. So how do you defend against that? That's as much just like any other software engineering workflow. It's as much a technology solution as it is a process and being aware. Then finally, you're going to deploy a model. And so deployment is the same thing or similar thing that you might think about in software. So you want the model to be able to be in a production environment. So it has to have all the same capabilities that you would expect out of a regular application. It's elasticity, scalability. It's that compliance if you have a regulatory environment that have to be baked into the deployment environment or production environment. So chances are that's going to belong to an IT or an architecture team that's used to doing this for a living. That's their job, and they're really good at it. So being able to make sure that your model meets those specifications is very important. And then finally, we talked about deploying it and making sure it works. Well, that requires some embedding of tools, tools for monitoring, tools for understanding whether or not the model is drifting. So is it still actually functioning the way you expect, both from a performance perspective on the statistical side, and also like, does it actually answer the business problem, right? And when you get to that point, what happens when an alert occurs? When a model gets to the point and a monitoring application tells you, well, no, it's not working. Does someone get paged? Do they have to get up in the middle of the night? What kind of tier of application is it? So these are sorts of, I'm talking like an IT person probably to a lot of people that are here, and they're like, well, what is this data scientist sitting up here talking about alerting and pager duty? Well, it's because some of these models have been deployed that I've worked on that have been in financial institutions. And if you shut down a financial institution's credit card processing system with a machine learning model, not only does it have an impact on the individuals, which is very bad for the company, but it can impact financial markets. So now we're not talking about a machine learning model and a creative, fun data scientist that's painting in a corner. We're talking about people going to jail. So these are really the things for production machine learning that we have to think about. And again, the good news is we have skills and understanding around this life cycle, but we haven't been thinking about machine learning in this context, and that's what we have to change. So one of the biggest issues that comes up is there are a lot of different skills involved. And the challenge that I've found, especially working in this field, is that the skills tend to overlap, so it's confusing who should be doing what. And so in our Birds of a Feather we did earlier, myself and Alice, we talked a lot about each individual organization having to figure out how they were going to sort of organize for this type of skill set. Who was going to be responsible for what, and where would you physically put these people? But at a high level, from a data engineering perspective, it's all about where you put the data, how you move the data, how you process the data, and whether or not it's accessible for the types of things that people want to do. So count analytics. Do they want to count cleverly or use probabilistic space, so data science and machine learning, and then also serving it in real time or near real time for scoring. So that's really a great place for data engineering. For data science, all the things we just talked about. So that starts usually with some kind of exploration tool, maybe a notebook, maybe like an editor like PyCharm. And then you have this like crazy experimentation and exploration thing that people usually do in pandas or R that is highly messy, but is still really important to making sure you understand what you're doing. And then finally, for production ML, once there's a model, you have to be able to do a lot of the things you did in data engineering, but with the last bit that I just talked about around monitoring, maintenance, and then also that hardening component. So these are the sorts of skills involved. So before we kind of go too much farther, what are we talking about when we say a model? I feel like this is a thing that is becoming like almost as buzzwordy as AI. So a model to me, and again, I'm highly opinionated, so apologies up front for that, is just a collection of code that represents a pattern of data, a pattern learned in data, that is served or is used to produce an output when given an input. So very, very simple. And this looks something very similar to what you might see in a production or a non-production data pipeline. You are looking at some representation of data. You may be doing something to it, like you're joining, or you're perhaps doing a transformation, changing the data, and then you're putting that back someplace. So that workflow is almost identical. But the ways in which you can do that, just like in data engineering, are really, really diverse. And so we're going to talk a little bit about how to deal with that and how to recognize where there might be complexity. I'm hoping that everyone has read this paper, because if you haven't, I really think you should. It's Google 2015, Hidden Technical Debt in Machine Learning. And basically what they said is absolutely true. About 10% or less of the actual machine learning code of a machine learning system is actually directly related to an algorithm. The rest of it is all the other stuff you have to do in that workflow that I just showed you. So think about it from a spatial perspective. If you're troubleshooting what's going wrong with your algorithm, and you've got to piece through all these other things, think about all the types of skills you're going to need, the time it would take, and quite frankly, what could go wrong. So it's important to make sure that you don't only focus on enabling the data science process. You definitely want to do that, but recognize that there's an entire ecosystem that goes into making this possible. And also, when you add complexity to this ecosystem, that technical debt compounds. And it's going to be harder and harder and harder for you to maintain that. So this is one of the many representations of the data science workflow. What I like about this one is it actually includes the data engineering component of capturing and storing and being able to make the data accessible. And sometimes it just starts with a data exploration. So ultimately, what we want to look at here is some of the challenges in this process. It starts off the fact that everything is heterogeneous. Not just the data, but the providers of the data, the storage locations of the data. Uh-oh. Looks like I'm getting kicked off the network. Storage locations of the data. Whoops. Okay, there we go. Wow, what is happening? I was gonna have to turn this off. Let me kill this, because I don't need it right now. Yep, that must be it. Okay. So the storage locations as well as the interface layer. So that's the, what you're seeing in Spark and Impala, SQL. And then when you start talking about that training layer, so this is, we're getting towards the right here, look at all the options that data scientists have to use or have available to them to be able to build and train a model. Now, if you're in a support function for a data science team or you're a data scientist and you're trying to remain compliant, you basically have, it's a soup, it's a mess. And that works out exactly how you think because, as I mentioned, there's not really a common representation of how to do this work. In the optimization and deployment phase, there's similarly a lot of options. But where things are really light is in the monitoring and maintenance phase. And that's changing, and we'll talk about that. But I want to give you a bit of an overview of the ecosystem that you're probably already working in or you will be working in soon. So the biggest challenge that comes in with having such a heterogeneous ecosystem is that these data science tools are designed to show you what the recipes are. So their whole point is to walk you through how someone created a data science outcome. So like a Jupyter notebook will take you from where the data comes from, it'll walk you through the frame, the feature engineering, and then it'll walk you through the training function, probably give you some accuracy scores, and then eventually it'll spit out a visualization that says everything is awesome, right? But the problem with that is that's not something that you can lift as a fully featured model and move into a software engineering workflow or data pipeline workflow. It's just essentially a recipe. And we're giving recipes to essentially data engineers who are not expected, they're not wanting to be chefs. What they're wanting to do is move the product. They want to get out there and make sure that people can eat. And what we really need to be thinking about is how to ship the cakes. And data scientists are just not good at that. That's not what we were trained to do. So some of the expectations of deployment is that you actually have the ability to test multiple models. When one model might be better than the other one, wouldn't you want to see how that works in real time? Well, those toolings are somewhat immature. You want to be able to deploy quickly. So I mentioned earlier on when we were talking about Google and Uber and the iPhone that there are actually paradigms or platforms to be able to deploy machine learning models very rapidly. And that's incredibly important when it's central to your business. So in summary, I'm not going to read you through all these challenges because we've kind of touched on them before. But the biggest issues tend to be around getting access to the information. Most data scientists spend a considerable amount of frustration trying to get access to the data, and most IT organizations have a considerable amount of frustration in restricting people who shouldn't have access to the data from doing crazy things. You certainly want to have flexibility in your tools. You want to have flexibility in your library and dependencies. But from an IT perspective, you want to make sure that you have controls over that. Dependency management is a huge deal from both a security perspective, and also it's a huge deal from the complexity of management. On the scale side, as a data scientist, I kind of mentioned this earlier in the keynote, I don't want to think about configuring resources. In fact, I probably don't know, I won't admit it, but I probably don't know what I should be using. Chances are, if I'm building a deep learning model as a data scientist, I say just all the GPUs, give them all to me, and I will train it, and it will work. But the thing is, I probably don't need them at all. And even if I did, I certainly shouldn't start with a job that uses all of them because it's extremely expensive. And also, they're hard to set up. And so most times, organizations don't even need to invest in that in the first place. So being able to have that capability set, but have it be elastic and have it be provisionable is certainly a capability that IT wants. But it's not something that is enabled out of the box. So parallelism goes along the same way. Parallelism, doing distributed machine learning, is a really powerful way to deal with large data sets. But writing parallel code is hard. It's been hard since I started writing code well over 20 years ago. It's still hard. So again, using things like Spark are a great capability to have, but that adds complexity. Remember that technical debt diagram? Now we're back, we're making that box bigger. We've talked about security, developer experience as well, but collaboration is something I really want to call out. So data scientists are really good when you have a plural representation of that group. They are really, really dangerous and bad when they're monolithic and siloed. So enabling collaboration should be one of the key outcomes of the IT and support organizations, right? That's the thing that you do with productivity software, that you do with enabling cloud software, Well, data science tools should be the same. But normally, like we talked about before, these notebooks or these IDEs are typically not a collaboration forward or first environment. So that's something to think about. And then we don't have to talk about deployment because that's all talk is about. So there are options. And one of the options is that you stop everything you're doing today and you invest millions of dollars in building a platform from the ground up that is perfect. And of course, in most enterprises, this is not an option. But I do think it's important to talk about because there are representations of what a future and a transformed business actually look like that have a lot of lessons for us. So if you haven't learned about it, Uber writes a ton about their Michelangelo platform. And what it essentially is an end-to-end machine learning or end-to-end data science platform or analytics platform that takes the process of building out machine learning models so seriously that everybody at the company who writes queries has to go through the training. And so it's a cultural transformation that they went through. It's a technology transformation that they went through. It's in the instrumentation of how they capture information. And then ultimately, like I mentioned before, they can deploy models immediately to production if they have that confidence. So great. Netflix, same sort of deal. They have so much information, they have so much instrumentation on how we all watch those shows that they can rapidly change the way that the front end is actually responding to the model itself. It's a lot of fine-grained control. And with Facebook, well, we all know that they still got some work to do on their algorithms, but certainly they're serving us with something. And that is coming from a pretty robust investment in the machine learning platform, FBLearner. So what do we do to get there? Because obviously we're not going to invest millions of dollars and hire a bunch of people to lose money for 10 years while we build a machine learning platform. It's not an option, right? So a unified data strategy is where you start, and that's why this talk is called Strategy to Implementation. We'll get into the tech stuff in just a moment. So you see the almost exact same diagram that we talked about before now represented into technical or operational terms. So the data engineering capability set should serve both your machine learning capability and your data warehousing. So this is like business intelligence and really fast queries as a part of the same set or same family of workloads. And I think that's very important because what I'm seeing today is a lot of data engineering teams are now siloing out a function to support machine learning. And inherently, you're taking away that collaborative support and the capability sets for the tools that you've built, and you're forcing yourself to go through a brand new form factor. And there's really no reason to do it. And what you should be enabling is layering on top of your machine learning tools, your BI tools, your editors, and your final data products. So this is serving data as a service or a product to users as a part of the same workloads. And then, of course, having a common platform for governance and security and the compliance component. So what I'm trying to say is don't work harder than you have to. So when we talk about model development, now we're going to talk about the menu that you have when you are going to be building out this. What turns out is that everybody has an opinion, but I got the mic, so mine's the most important right now. No, I'm just kidding. But I think we've kind of alluded to this a little bit earlier in that the development component of machine learning is really diverse. You can use PyCharm, RapidMiner, RStudio, KNIME. There's a million different options for development. But there are some key principles that are required for you to get to that enterprise capability that we've been talking about all day. And the first thing is that collaboration and code reuse have to be at the top. If you're building out a capability set that can't be reused, what's the point? So I really do think that when you're doing your evaluations of machine learning platforms, even when your data scientists are a part of it, everyone should come to the same agreement about that being at the top of the list. The second is open source frameworks and libraries really should be invested in. And the reason for it is both a business reason and also it's a security reason. Business reason is, well, you don't want to get locked into a single toolkit. And also you're going to miss the layers of innovation that occur when the open source community collaborates on projects and libraries that are really important. From a security perspective, everyone gets hacked. So if you lock yourself into a single framework, you're vulnerable immediately. Your entire platform is vulnerable. And it doesn't allow you to mitigate the deployment paradigm. So you want it to, from an IT perspective, really make sure you handle dependencies and isolate the development environment. So isolating the development environment is something that is pretty easy to gloss over. But what I'm saying is you want to isolate the workloads. So let data scientists be data scientists. Let's go off and break stuff. But let us break stuff in our own house, is basically what I'm saying. And then finally, that elasticity is something that's extremely important. You want to be able to scale up when you need it and then release resources when you don't. And finally, and I'm underscored and bolded, if your editing solution or your development solution requires you to move data into it, you're probably already in a bad space. And the reason is because it's very expensive to do, and also the data pipelines to support it are another area of brittleness that you can put in place. So training and experiments. So I think this is something that is a unique component of machine learning development. So in a software experiment, an A/B test, or software application, an A/B test is really easy to do. You just put the UI up in front of a customer, and then you let them click around, and then you see whether or not it actually increased the behavior that you were trying to do. But that's not good enough for a machine learning model. There are two different areas of evaluation that you want to have. One is the model's performance. So is it still, from a statistical perspective, so like let's say it's a classification, you'll hear things like F1 score or precision and recall. Are they still meeting those metric thresholds that we've come up with? And that's the data scientist's responsibility. Now, on the other side of things, it's the business rule. Are we actually lifting or finding some lift in the business outcome that we care about? That is a business or a line of business responsibility. And those people are not normally even in this conversation, right? So when you're building an experiment or you're designing an experiment platform, remember that you've got to serve two different user populations, and they're going to have very different interactions with the data. So experiment management. So from a data science perspective, that first side of things, so statistical evaluation. So data scientists want to take a look at every single thing that they've done over history and find the points in which they're seeing changes to the model's performance. So this is essentially dependency management or version control, but it's actually applied to the process of training a machine learning model. So think about this in a practical sense. So when we build ensemble models or even deep learning models, there's this concept of parameter optimization. So there's a lot of different tweaks or levers that you can pull to make a model fit toward the data and actually have an accurate representation of what's happening. In deep learning architectures, these can be hundreds of different optimization parameters, sometimes thousands. This makes the model very big and complicated. And if you run 3,000, 5,000, 10,000 different runs of experiments, and you drop the last 1,000, and you found actually that the best model was in one of those 1,000, then how do you reproduce it? So having granular experimentation, version control, and the ability to instrument what's happening is super important. And this is an area that's, quite frankly, pretty immature. But there are some open source and also proprietary tools that are starting to take a look at this. Also, CDSW, as a shallow plug, is doing this as well. And we're really investing a lot of our own engineering time because it's a huge problem, especially for enterprises who are building lots of models in different ways with different lines of businesses. Okay, so we're getting farther in there, into deployment. So deployment. It turns out that there's not just one way to deploy things. And I think that seems obvious, but mainly what we end up seeing with data scientists, especially because it's easy and we're not necessarily the most mature software developers, is the API-based model. And that's great, but there's a lot of other ways to do things. And the first, I think, and easiest, probably most common, especially for the first nascent use cases, is about batch scoring. And we talked about that earlier. It's just a job that you're running over time. And chances are, if you really understand what you're doing, you can make that job extremely efficient, and you can make it very, very easy to understand. So that should be the goal. Let's be clear. If you could do it that way, solve the problem like that. There's no reason to build an extremely complex API-based application, and if all you're trying to do is run a Spark job, right? Or running a job that is running some C code. Let's start about that. Let's start there. Now, if you need to essentially automate some internal decisions, and you need real-time scoring, like for example in fraud detection, you might want to think about using an API-based solution. When you get into real-time scoring and online scoring with sub-second response times, this is where you need a data flow solution and some custom monitoring. And then finally, at the edge, when you're embedding machine learning into devices, so this is the sort of thing that I was trying to do at Fitbit, there are specific requirements around the model's performance on resource limited machines. So think about it as the Apple Watch, or think about it as your cell phone. Very limited amount of compute, memory, and storage available. They're extremely optimized for power consumption. So chances are your model is not going to be able to spike to the amount of resources that it would need, even if it was available. So you've got to be able to operate in that environment. And that's a different deployment paradigm. So how do you think about this? Well, this is not an exhaustive list, but it's an interesting matrix that I think can be useful when working through things. So on this axis, there's technological benefits and cost. And as you think about the most expensive thing that you could possibly do, what actually a great technological benefit, it's, well, rebuilding the whole thing in Python. Because Python, right now, at this point, is becoming, really rapidly becoming the most extensible language for machine learning and AI. And there's a lot of investment. There's a ton of community involvement. But because it is not optimized for things like dependency management, it's expensive to maintain. So yeah, that's a really good outcome if that's what your company is built on. But chances are you're going to have some kind of hybrid model. So the API-powered model is a way to get away with using these types of tools, but to expose them in a way that any type of language can consume or any application can consume. So this is the idea of something like a RESTful endpoint. So you build it in whatever you want, even R or Python, and then you create an application, maybe a Flask application, very, very small, very lightweight, and you call that application programmatically from another application or another workload. And then basically what you're providing is an input, and it gives you the output answer. And you can do whatever you want with that in a programmatic way. Another way to kind of think about things as you get into the rest of the matrix is talking about the hybrid approach. So this is when you look at representation frameworks, so like Onyx or PMML. What these are a non-code or low-code based representation of models. What that means is you're not writing the specific code or specific architecture for each model, but you're representing that, for example, saying, I want to run a random forest with these parameter settings, and I want to be able to input this kind of data. And you're putting that potentially into a text file, like maybe YAML or XML. And you're using that as a way to move your model representation around without actually encapsulating everything into a file or encapsulating everything into a project, and then running it in a different compute environment later. That's the way to do it. And then if you want to go really fast, but you have to really understand your model, and you have to be a great programmer, or have great programmers, you could rewrite the entire thing in a more performant language. And this happens all the time, but it's very slow. All right, so monitoring. I think we've kind of talked about this, but I want to kind of talk on what the monitoring mechanism needs to be. And the most important part is that it's agnostic of the model type. And that means it actually has to be robust for different types of encoders. And the reason it needs to be agnostic is, again, the theme is to be able to rapidly deploy different types of models as a part of your business. So if you only have a monitoring solution that works for random forest, and then you all of a sudden deploy a recurrent neural network, and it can't be robust to that, then you've got a part of this technical debt that you're going to have to write in to make sure that you have the same capability. So you want to be able to instrument the data flow in and the model performance out. So it's not just about how the model performs from that statistical perspective. It's actually, do you have the right data, and does that data actually look the same over time? And so you also have different types of not only parameter settings, but also model performance and accuracy metrics. So things like RMSE, MAE, I mentioned for classification F1, and things like that. So now I'm going to transition and talk about what we think about it. So from a Cloudera perspective, we've been investing in a platform for a really long time. I don't think that's news to anybody here. But what I've talked about for a while is that a lot of the same types of workloads that you need to do to support machine learning and AI are the same ones that we've been doing for years in data engineering. It just needs to be applied to the context. And how we've tried to do that from a tools perspective is what I showed a bit earlier, which is on CDSW and later our Cloudera machine learning product. Now, what I will say, and this is where my team, Fast Forward, gets involved, there's no way to solve this problem with technology alone. It's about process change, culture change, people, and also algorithmic excellence. So chances are your team will actually have to have some really strong individuals across aisles, across the data engineering, machine learning, engineering, and data science groups. So this is a representation of how things could work if you use the container architecture. And it happens to be what CDSW does. Also, quite a few other individuals use that as well. So there are things like sessions, jobs, experiments, and models that can all be encapsulated in different types of containers. Basically, if you're not familiar with containers, it's a way to represent the important components or important frameworks of a machine without delving into the underlying hardware requirements. So VMs are very, very heavy because you have to essentially emulate how the hardware works. And containers actually go above that and work on above the OS layer, or at the OS layer and above. So it gives you some power to be able to represent these types of capabilities really, really quickly, spin up resources, and then manage those resources using an orchestration tool like Kubernetes, and then deploy workloads as opposed to deploying individual strings of code. So lots of research to be done about containers. I'm not going to give a container talk, but this is sort of the background to a lot of the way things work. And it looks like we might be out of time, but if we can do it for a second, I will show a quick demo of how that works. And hopefully the internet is back on. If not, I will use my phone. I give these talks a lot, so I know how to break through the problems. Here, we're good, we're up. All right, so I've showed off a lot of this earlier, so I'm just gonna really quickly start this up. What we did was actually build a set of models. I don't think I did that. It actually worked. Let's see if I can get this back up here. Come on. So what we did while it's loading is build a set of models that basically inputted data from the New York City traffic data open API. So it's real-time data that was collapsed inside of our NiFi tool. And then we were able to build a set of machine learning models using this tool, CDSW. Oh, here we go again. Using this tool, CDSW. Oh man, if it's down, that's not gonna be fun. Ah, there we go. Hang on one moment. Definitely should have gotten the internet working beforehand. All right. Well, if I can't show you in real time, I will show you with slides, which is less fun. But I have them. Let me unshare these. Let's skip these. Okay. All right. So what we built, which I would love to show you if I had internet access, is essentially a way to pipe in data, to process data, and manipulate the data for machine learning. Here we go again. Turn it off. Okay. And then finally, deploy it into a production workflow, just like we talked about in the earlier part of the talk. So what we believe in Data Science Workbench is really to deal with some of the same challenges that I talked about before. We want to make sure that data scientists have the ability to experiment, collaborate, and deploy with confidence without having to go through the pain of provisioning and building out a production application. For IT professionals, we want to bring the data scientists to the data, but not make them move the information, make sure it's secure and compliant, and then we run it anywhere, whether it's in private or public cloud. So the models function in CDSW, which I was going to show you, basically allows you to define a workload. So this is a containerized machine learning capability. Define the parameter inputs and outputs, even run tests inside of the deployments, and then finally deploy those into repeatable workloads that can be launched anytime via jobs. The experiments gives you that lineage, that history that I just talked about, of being able to understand what the runs looked like over time, and making sure that the data scientists have the ability to isolate either what went right, what went wrong, and reproduce that at any time. And then finally, the model management tool is really important. It gives you that revision and version control around being able to manage the model through the entire life cycle and be able to promote and demote models as they serve. And then this is the jobs function, which I alluded to earlier, which allows you to do orchestration around batch scoring, and then also you can use the models function to deploy to that API endpoint using that RESTful solution. So this is the summary. It's really the same thing I just said before, which is end-to-end workflow support, collaboration built in, security from the ground up, and then allowing that openness because it is based on and continues to be really responsive to and based on open source technology. So that's me. Sorry about the Wi-Fi, but if anyone has any questions, we have many of these demos running online, and a lot of times I post about them and talk about what we're doing. So that's what we got.